welcome back to my channel and the Open Source Cafe podcast. We have a returning guest, Lane from Boot.dev. For those of you who don't know Lane, he has an amazing learning platform, Boot.dev. We did a podcast on it previously around Lane's experiences and stuff. Lane, really nice to have you back on the show. Would you like to tell our new viewers a little bit more about yourself because it has been a while?
Yeah, love to be here. Super excited to be back to talk a little bit more about some DevOps stuff. I think last time we chatted more about learning to code and starting a career in programming. But in my career, I started as just a backend developer, and especially after just a couple of years, I started doing a lot of DevOps work. And kind of my personal belief is that kind of the best backend engineers learn a lot about DevOps. The best DevOps engineers learn a lot about backend or development so they can do more automation. I think the two work really well hand in hand. So it's one of my favorite topics to talk about. And like Kunal said, I'm the CEO of Boot.dev. It's a learning platform for backend engineers and DevOps engineers.
Amazing. And for folks who want to check out Boot.dev, you can check out, just go to Boot.dev. That's it. I don't even have to say check out the links in the description, but I'll still add it in. But today we're talking about message queues. I don't know how we got onto that topic. I think I made a video. Did I? Or was it a blog post that I did?
I can't remember. Something that you said piqued my interest because I've worked with a ton of message queues, and I was like, we should talk about this.
All right. That was I believe it was a blog post. So you can go to blog.wemakedevs.org. We are We Make Devs now. We've rebranded. So exciting things are happening. Let's talk a little bit more about it. Let's start from the very basics. For someone who might not be familiar with it, what essentially is a message queue in layman terms? Explain.
Yeah, so it is what it sounds like. It is a queue of messages. So if you're familiar with the idea of a queue, right, which if you're from England, it probably is even easier because I think they use the word queue when Americans use the word line when we're talking about lining up for something at an event, right? But it's basically a kind of a first in, first out structure. So you put 3 messages in. Whoever the receiver of those messages will receive those messages in the order that they came into the queue. Right, so message 1 goes in, then message 2, then message 3. The receiver on the other side will receive in that same order message 1, then message 2, then message 3. So that's like the very basic idea of what a message queue is, and it enables some really interesting things as far as communication goes on back-end systems and servers.
Amazing. And can we talk a little bit more? Let's talk a little bit more about when would one want to use a message queue? And you mentioned that you have worked with it quite a lot. So I'm here to learn from your experiences. Yeah. Tell about what are the scenarios in which you found yourself in a place using one?
Yeah, so I've spent most of my time with message queues has been spent on RabbitMQ. So it stands for Rabbit Message Queue. I'm actually the maintainer of a reasonably well-used open source piece of software called Go RabbitMQ. You can check that out if you're into Rabbit. But there's some let's talk about kind of the 3. I would call them probably the 3 pillar technologies that you'll hear about when message queues comes up. So RabbitMQ is a really popular one. There's another one called Kafka that I've used as well, Apache Kafka. And then Google has a proprietary solution called PubSub that I've used. That Boot.dev currently uses on its backend. And one that I have not yet used, but I'm somewhat familiar with, is SQS, which is an Amazon product. And I'm sure there are many more out there. Those are the 4 that I'm most familiar with. And your question about why would you use one of these products, this is really, really important. So typically when you're working in the kind of the back-end side of a web architecture, you'll have multiple services that need to communicate with each other, right? So you may have, and this is, I'm kind of implying or presupposing that you have some sort of a service architecture. There are obviously simple backends that are kind of monolithic in nature that don't need to talk to each other. But typically, as a architecture grows, right, as your company gets larger, even if you aren't running like a strict microservices architecture, you likely will have some kind of services architecture where things need to talk to each other. Just as the company grows, that almost certainly happens. And when those services need to talk to each other, usually the simplest thing to do out of the gate is just to use HTTP, synchronous kind of HTTP requests between servers. So you have server A, say, that manages like users, and then maybe you have server B that manages like, let's pretend this is a social media application, maybe it manages the tweets. Those services will need to talk to each other, right? And they can do that just via, get, post, put HTTP requests. The interesting thing about message queues is they allow these services to talk to each other asynchronously, right? So service A can publish a lot of messages about what's happening in the world. And when service B has time, it can acknowledge all of those messages and process them. You can't do that with a synchronous protocol like gRPC or HTTP. Everything has to be done kind of at the same time. If you send one message from server A to server B has to process it immediately. And then, what would happen is server A would get the response, and then it would send another message. So message queues allow us to queue those messages up in a line so that they can be processed kind of, when the receiving server has compute capacity or memory available or what have you.
Yeah, and since you mentioned about like, let's say, asynchronous nature and it's first in, first out. So what about scalability? Is it like easy to scale because the messages are independent of one another? You just so what if you want to like scale, for example? So are there any limitations to it or
Yeah,
yeah.
that's a great question. Let me walk you through just a very high level overview of an architecture I worked on at a past company. So we had essentially, we called it our data pipeline, where we were processing hundreds of tweets per second, doing like natural language processing and stuff on these tweets. And every little service in the data pipeline, which were just individual Go applications, had their own little job to do. Like, for example, one might check whether the sentiment of a tweet was positive or negative, right? Whether the person's like happy or angry in the tweet that they're making. Another one might sort the tweets by topic or something like that. So we had all these little services, and in between every service, we were using message queues. Specifically, we were using Rabbit. And the reason this mattered is because we were doing such a high volume of messages, like as you mentioned, we needed to scale. The great thing about message queues was if something went wrong with a server right in the middle of the pipeline, it wasn't like everything would break. What would happen is all of the messages going into that server would just start backing up in the queue. So when everything was healthy, most of our queues had 0, 1, 2 messages in them, very few messages, right? Because they were being processed and published at about the same rate. But when a service had a problem, or maybe, I don't know, Elon Musk tweeted, so there's tons of volume coming in, right? Then the messages would just start to back up in the queue. And as we auto scaled our cluster, right, using Kubernetes, we could scale up the number of pods for that service. We'd be able to catch up and get back to real-time processing. So as far as scalability goes, yes, absolutely. The message queues were a key part in ensuring that system could scale. Had we been using gRPC or HTTP for that system, there would be nowhere for those messages to live while they're waiting. They would have been living in memory on every container, which if you restart a container, now you lose everything in memory. There could have been all sorts of potential issues.
Yeah, so you mentioned, let's say, about like using a message queue. So what if it fails? Like you use RabbitMQ. What if RabbitMQ fails? What is going to happen to the messages that were in the queue?
That's a great question. So in this particular architecture I'm describing, it's funny you bring that up. RabbitMQ is essentially our like largest blast radius point of failure. If RabbitMQ went down, like everything, like nothing else would work. The good news is RabbitMQ, Kafka, PubSub, like all of these systems, at least the ones that I've used, are distributed systems. So very frequently we would have a node go down. So we have our Rabbit cluster of, say, 7, 8, 9 different servers all connected to the same cluster. Very frequently, we'd have like hardware failure, network goes out, something goes wrong in the data center, and 1 or 2 nodes goes down. Luckily, that never actually resulted in a significant outage. We never had the entire cluster go down due to a problem like that. So that's kind of the nice thing about working with these distributed systems like Kubernetes and Rabbit is they're designed to be fault tolerant. I mean, there's definitely still ways in which things can go catastrophically wrong, but as long as you're being careful and you're kind of distributing load correctly across the nodes, you can mitigate almost all of those concerns.
Nice. So from where you are, like from what I heard, and from what I've done, like for example, if we talk about some of the other challenges, so like maybe you need, so you're talking about message queue, like okay, this finishes, then we have the other one, then we have the other one. So if you're using like something like if you're using a shared memory, for example, so in that case, let's say you're working with, you mentioned tweets. So tweets are like not that like that in terms of data, it's not very big. But let's say you're processing GBs of data, for example, right? Now in the message queue's memory, that's going to take a while, to copy it and then into a single message queue and stuff like that. So does it make sense to use a message queue if you want if you're working with a large amount of data and you need that speed? Because I know it's more secure because yeah, if you have multiple processes running, it's not going to override all these things. um, but my question is like if you're concerned about having a huge chunk of data and speed, should we go for message queue or something like a shared memory?
That's a great question. I can think like where I would like if this problem were presented to me at work, like where I would start, but I can't tell you what I would do because I haven't actually done it. But what I would do, like what I think I would do, or at least where I would start, is when you're working with very large amounts of data, you don't want to overuse your IO, like your network bandwidth, right? So in the system that I just described, say we had 5 or 6 services in a row, they're all doing their little bit of processing on the data. If every message were a gigabyte in size, we would have to process it on one server, send it back to Rabbit, and then send it back to the next server, then send it back to Rabbit, send it back to the next server, and then back to Rabbit, back to the next server. So like that's a lot
what
of
I was
bandwidth,
saying. Yeah.
right?
Yeah.
So I would definitely worry about that. And like you said, shared memory could definitely work. Shared storage could also work. You could also take those services and kind of bring them all together. Like you wouldn't necessarily need them all to be microservices. You can make them more of a monolith that does all the processing at once. Anytime data starts to get large, I start to look at solutions like S3 or like cloud storage buckets. It's like, how can we grab the data out of the thing that it's stored in, do all of the stuff we want to do to it, and then put it back? Those are the kinds of things I'd be worried about if I was processing very large files.
Yeah, I think that's the only advantage that a shared memory would have in terms of with message queues, which is if it's a large number of data, a large volume of data. But you mentioned microservices, so the follow-up can be: does it only make sense for microservices, or?
Yeah, that's a great question. One of the great things about having kind of a pub sub architecture, which is like this asynchronous architecture, is how flexible it ends up being. Like you can use a pub sub architecture with a monolith, and then as you grow or maybe break out parts of the monolith, you don't have to change your queuing system. So for example, let's say that you just happen to work at a company let's say it's a fairly small company. You have a monolithic backend, just one giant, Go or Java or Ruby on Rails application. If you have a monolithic service, very often you can do kind of message queuing in memory, like literally just using like arrays and lists, or in Go, you could use a channel or something, especially if you only have one instance of the server running. And that like will work for some amount of scale. As you get bigger, almost always what happens is you have your giant monolithic server and you go, okay, like we're sending a lot of emails. Like we need to break out the section of the code that's doing all that email IO and just put it somewhere else, right? And the nice thing is if you were already using some sort of asynchronous queuing system on like behind your server, now you don't need to make too much of an architectural shift. That is the approach I took with Boot.dev. It is fairly monolithic at the moment. There's kind of one large Go server. I've broken out like one or two little pieces, but behind the scenes, I'm using PubSub to do almost everything that should be asynchronously. Let me give you like a hard example of that so that this makes some amount of sense. In Boot.dev, you earn experience whenever you pass off an assignment. So you get some coding problem right, you earn 100 experience. I have several systems on the back end that care about you earning experience. For example, I need to level you up if your experience goes above the threshold that would give you the next level. Maybe I need to give you an achievement, right? Maybe I need to send you an email if you unlocked the achievement. Like there's all these things that can happen when you earn XP. Maybe you get a Discord message, right? Congratulating you, something like that. So the nice thing about an asynchronous system is you have your publisher, the service that's awarding XP, just publish a message to the world, right? To the entire universe, as far as your backend is concerned, that says, hey, Kunal earned 100 XP. And now all the other services can get their own copy of that message and do whatever they want with it. So like maybe I have an email service, it gets that message, Kunal earned 100 XP. And it can decide at that point, do I need to send Kunal an email about this or can I ignore it, right? And maybe most of the time it's ignored, but maybe one time you level up and so we're going to send you an email. So it's really flexible in that you get this really clean break when you use asynchronous publishing in the right way. And maybe later we'll talk about when you shouldn't use it. But when you use it in the right way, you get this really clean architecture where an event happens and other things in your architecture can respond to that event in the way that just concerns them. It allows you to think about little sections of your architecture in very isolated units.
Decoupled,
yeah.
Yeah, that makes sense. So like we talked about, the scalability is one of the advantages. We can talk about like, so for example, if it fails, you mentioned that it will just, it will just, it will still continue.
Kicks it back onto the queue.
Yeah. It will still continue to function. Cool. We're talking about like, we were talking about, like you mentioned, when not to use it. So maybe we can touch upon it right now. So
yeah. This is a great topic. You'll see a lot of these like controversial threads about microservices and message queues and asynchronous stuff on like Hacker News, right? Where people get really up in arms about like, yes, you should, or no, you shouldn't use it. Where I've landed after several years of working with these systems is they're great for what they're great for and they're not great for what they're not great for. That usually tends to be the answer with a lot of stuff in engineering. What message queues are great for is kind of what I just described, I think, where like an event happens in your system and you potentially have many other parts of your system that care about that event. So like a one-to-many fan out of essentially like event responses. Asynchronous publishing is really great for that kind of a thing. The problem with asynchronous publishing is it's fairly complex, right? It's not like you can just turn on a button and all of a sudden your architecture will have this amazing like asynchronous, flow going between all your services. It takes a lot of time, a lot of work to get everything up and running smoothly. If your team isn't familiar with RabbitMQ already, you're going to have to train everybody up on RabbitMQ, right? Or PubSub. You're going to have to install and configure those clusters. Now, depending on what solution you go with, for example, my last company I worked at, we used RabbitMQ and we manually managed it. So we used Terraform to stand up all of these nodes. We used Ansible to configure everything and get it up and running. And then we manually connected all the networks. At Boot.dev, I used PubSub, which almost literally was just turning on a switch and using it. So, different solutions are good for different things. Also, PubSub is almost certainly more expensive. But I guess my point is there is a very high complexity cost with asynchronous messaging. So I guess my advice is typically, if you can get away with it being synchronous, do that as long as it's working and isn't too complex, right? Once the synchronous messaging starts to get really hard to reason about, right? Like this event happened and now I'm synchronously sending 5 HTTP requests and I have to make sure they all come back and, acknowledge them manually. That's when I think starts to make sense to thinking about, to think about implementing one of these kind of larger asynchronous tools.
Yeah. And what is the format of data that you use for message queuing systems? Is it JSON or?
I've primarily used JSON. There are others, of course. At the end of the day, all these systems just work on bytes, so you can send whatever you want. I will say the advantage to using JSON is that when you are manually debugging something, it's human readable, right? You can grab a message manually off of the Rabbit cluster, look at it, say, what the heck is this thing? Should it be here? All that kind of stuff. When you move to a more typically the reason you'd move away from JSON is because you can get better compression. You can get more efficiency out of a different system. And usually what you're giving up is human readability in that case. So that's really the way I'd think about it, is like, if you have the bandwidth to do the human readable JSON thing, I do that as long as you can, just because it's going to make your life easier. But at a certain point, you're sending enough messages that it's cost inefficient to use something like JSON, right? So you might look to use something a little more compressed.
Yeah, making things easier to debug. I think that's also one of the things that asynchronous the practice also helps with, like making it easy for folks to debug and stuff. Cool. And in the beginning, you mentioned about gRPC. Is there like any relation between that and message queues?
Yeah, kind of. I think a lot of times, they're used for the same thing. So people will sometimes compare the systems. The way I would think about gRPC and message queues is very similarly to kind of how we talked about it maybe 10 minutes ago, where gRPC is a synchronous system, just like an HTTP request. So if you're interested in synchronous requests, gRPC will work great until it stops working for a given system, in which case you can implement something asynchronous like RabbitMQ, Kafka, PubSub. What's the more interesting discussion, I think, is about whether you're going to use just plain HTTP request response versus gRPC, because they kind of serve that same purpose of like synchronous request response kind of network calls. And I think most of the time, if you're working purely in the backend space, gRPC is a great option, because you get kind of type safety and all these other kinds of things that make the development experience better. However, a lot of times it's just way too much work to try to get like a gRPC or an RPC system working between like client and server at all, and so you're kind of limited to HTTP in that regard.
Yeah, I think that's true. In simple terms, maybe we can say that if you're using like a one-on-one service, maybe you can use gRPC, like for like more like inter-service calls. But if you're having like a lot of tasks that you need to queue, or let's say you don't really care about which service is going to consume the message, like where is it coming from. So for example, if you talk about emails, so you have like 3 services that are sending or like triggering email, like for example, like I don't know, password reset, newsletter subscription, and one more. And then you have your queue, and then there's a collector that sends it to the people, right? For example, so that collector thing that doesn't really care who is sending the email. So in these sorts of scenarios, I think message queues.
Yeah, absolutely. Anytime you have an event to publish to the rest of your services and you don't care who's acting that event and doing something with it, message queues is fantastic, because the only alternative with gRPC would be, okay, I'm going to send 5 remote procedure calls at the same time, right? I have to like multi-thread these calls to make sure they all happen at roughly the same time. I'm not doing them, all one off in order. Couldn't agree more.
Yeah, and when we have buffering, for example, in the stream. So gRPC is like, it's a messaging protocol, so you can't have buffered data.
Right.
But you can have it in like message brokers. You can store stuff like that.
Yeah, there's a level of persistence there, right? That's a really important point. With gRPC and HTTP, there is no like technology in the middle. There is no Rabbit server, Kafka server, PubSub server that can actually store messages for you. If your RPC call fails, it's on you as the producer of that message to do something about it. Maybe you write it to your own database, maybe you retry. If you have that piece of technology that's doing it for you, your application code gets a lot simpler, right? You can just produce the message to Kafka. If Kafka isn't able to send it to the consumer, Kafka deals with it. Kafka puts it on its message log, stores it there for you. It does simplify a lot of that kind of stuff.
Yep. Cool. Well, thanks a lot for sharing, Lane. My just one last question to you is like, can you share maybe from your experience some of the common pitfalls that developers make when like using message queues for the first time? Are there like some scary propositions like messages being processed twice and things like that. So how can folks be mindful of that and
Yeah,
using it for the first time?
absolutely. Probably the biggest one I ran into when we like onboarded new developers was not thinking about like infinite I call it like the infinite knack loop, where essentially a consumer is pulling a message off of a message queue, trying to do something with it, failing, and putting it back on the message queue, and then grabbing it again, trying to do the same thing, knacking it. So like imagine that like a message in your RabbitMQ system is like badly formed JSON. It's like invalid JSON. You could have some code that tries to grab the message off, parse it as JSON, it fails, and it throws it back on Rabbit and then just grabs it again. And so you get into this infinite loop where you're just burning CPU cycles trying to process the same message over and over, but it's never going to work. There's something wrong fundamentally with the message. So I think that was probably the biggest pitfall we ever ran into, and the answer to it I think is like you come up with some sort of like sane retry thing, right? Like I'm going to try to parse it, and at most I'm going to retry this single message like 5 times, and then you can also break it down by the way in which things went wrong, right? If you tried to parse JSON, it failed to parse, it's not going to parse the second time. It's just never going to work again, right? So you probably have to do something special with that message. Maybe you write it out to a log, mark it as an erroneous message. The only time you want to like knack the message and put it back is if you have a like reason to believe that on the next try, it'll actually work. So say network is down. Well, maybe the next time I retry, we'll have internet connection again. So that's probably the biggest thing is infinite knack cycles.
Amazing. Well, thanks a lot for sharing, Lane. It was really great talking to you. Got a lot of nice, fun discussions, and discussed about a lot of things. So very, very, very engaging podcast. I had a lot of fun.
Thanks,
All
Mel.
right.
This is awesome.
For folks who want to learn more about it, you can check out the links in the description. Just one last time, you can check out Boot.dev. Some pretty nice courses there. I'll link Lane's Twitter and stuff in the description below as well, so you can connect with him later on. And if you liked it, you can share about it on socials. You can tag us. You can share what you learned, and would also love to share your views. If you disagree with something we said, go ahead, share it. Let us know. I'm hoping to have another good discussion. But thanks again for giving your time, Lane, and hopefully I'll see you in the next one. Yeah.